the finite energy solutions involving just scalars in dimensions greater than 1 plus 1. Okay. So the thing is we have already seen one example of vortices where we went around, we got around Derrick's theorem, we got finite energy solutions, and the thing is, but I did not explain why that happened, and the Hooft monopole also fits in that category. It is time independent, we are looking for finite energy, or we will be looking for finite energy. So what we will do now is to ask the same questions again, and also in the process derive the boundary conditions. I only derived one condition yesterday, which was to say that when r goes to infinity, the value of the magnitude, so the phi square should take whatever is the minimum of the potential. Okay. So let us go back to let us work with 3 plus 1. I will come back to 2 plus 1 to explain why even the vortex thing works. So we will be in 3 plus 1 dimensions, and let us choose like we had the exact same setup. We will have a triplet of scalars, so 3 real scalars which are in the adjoint of SU2 Samgul. Okay. And so the Lagrangian is just the usual thing, but let me write it. I will keep going back and forth between writing it as a column vector or this thing. So let me write something here, because some formulae become compact. Okay, I should maybe put a transpose, or oh, this will do, I think. Yeah, this should do. Yeah, this should do, where phi is just the usual 3 guys which we had, phi a sigma a by 2. Okay. These are real scalars, so I do not need to put star and stuff like that. Okay. And we will have a u of phi, and u of phi can be exactly what we chose earlier, which was written in a slightly different form. So let me write that. And let us write it like this. Okay. So this is the usual quartic potential that we know, and this this thing has a minimum when mod phi square is equal to a constant, and that constant is the minimum of this potential. Okay. What was that minimum? It was some mu by lambda, mu square by lambda. Okay. So the idea is that we look for, we will do what Derrick said cannot be done. We look for time independent finite energy solutions. Okay. These cannot exist, but before we get to before we get to this, we will see that there is a topologically conserved current Okay. So, in other words, by this I mean something which is conserved without using equations of motion. Okay. So, I will not put an equal to right now, later we will put an equal to this thing J mu topological, which I will write as epsilon mu nu rho sigma trace of d mu phi nu d nu d rho phi d Okay. So, just so this trace is put because these are this way, when you write it this way, these are matrix valued guys. Okay. And because of the antisymmetry between these things, I could even write this thing as a commutator of these two guys, okay, with a half or whatever. So, let us even do that. Let us put a 3 factorial here to take care of certain combinatorics, and so we can define, so J0, so there will be a Q which I will define with some constant which we will fix in a moment, times integral d cubed over all space, and put mu equal to 0, it becomes just epsilon ijk. Okay. By the way, is it obvious that this current is conserved? It is, because when you do d mu of this thing, you will have 3 terms, but each one of them will, I mean, you will have d mu d nu of phi, which is, this is antisymmetric and that is symmetric, and so it vanishes. It's the same argument as before, and so for each one of these terms that is indeed true. Okay. So, so while we are at it, we can also write in 2 dimensions, in 2 plus 1 dimensions. I can write a similar J mu topological, which would now just be similar to this, but only 3 such guys. Okay. So, one might think that this could be any phi will do, but now for instance, suppose I had just 2 scalar fields, this what will happen to this kind of a charge? If you look at the derivatives, okay, if there are only 2 scalar fields, there will be only it follows effectively that whatever you do, like I said, there is an antisymmetry in the problem. You will find that there cannot be, there is not enough space. Okay. So, you will need at least 3 scalar fields. You can have more than that, that will be okay, but so that is why we needed these 3 real scalars. A similar argument will tell you here that you need at least 2. If you write them as phi 1 phi 2, you will see that you can write something and antisymmetrize. If you antisymmetrize 2 identical objects, it is 0. Okay, there is not enough space. So you can see that even though I am writing a trace out here, I mean, and with 3 I could have done it with only 2. Okay. Again, you can see that this is conserved for the same reason that this was conserved, and you can go down to 1 plus 1 dimension, and you can just make do with 1 scalar, 1 real scalar. Okay. And homework exercise to write the ones in greater than 3. Okay, it is not too hard. Okay. So, coming back to this problem, it tells you that there is this kind of charge which might be possible, and so we are going to choose it to be what we have considered here. So, now the point here is that this is a total derivative. Again, you can see that because I can pull out this di, any one of these guys, I can pull them out, and when it acts on it, when the derivative acts on the other 2 terms, it would be again for the same reason that this vanishes, that would vanish. So, this is really a total derivative. So, this particular charge can be written as a surface integral. Okay. So, Q topological. So, now this is just as a reminder of the other things, we will continue with this. So, Q topological will be some constant divided by 3 factorial times, should it be 3 factorial or 2 factorial, does not matter, that we can absorb in the constant. So, I could write this as a integral over the sphere at to infinity using Gauss's divergence theorem, because we are just in normal 3 dimensions times dSi okay. So this is just because it's a total derivative, so it's going to be this way. Okay. So now coming back to the setup, let us ask, can we write time independent finite energy solutions which carry this charge? Okay. So let us look at the Hamiltonian density for this thing. Okay. So now the point is there would be a time derivative parts, because it is time independent. I am just saving time, I will not write the thing. So I am just going to write out the spatial parts. It would be di trace of di of phi okay. So now let us write out the conditions for finite energy. So these are boundary conditions if you wish. So at, of course, r tending to infinity, first thing you require is this u of phi go to its lowest value, and remember there is a constant here which we need to add so that the infinity, boring infinity is removed. So we let us assume we have done that. So we need mod phi square, this is something we discussed yesterday, should go to mu square upon lambda. Okay. That takes care of this term. So this term vanishes quite fast, let us say. Okay. What about this? This tells you that you are in 3 dimensions. So this better at least go like 1 by r power 3 by 2 plus some epsilon. Okay. So if it goes like exactly 3 by 2, it will become the radial integral will be r square dr divided by r cubed, so it will be 1 by r. So it will go away from the log and then you are fine. Okay. So these are the two conditions that you require for this thing. But now let us ask, what are the conditions? So now that we have written this topological guy as something at infinity, so first thing you can see is that this sort of fixes this guy to go to some constant value. But now we have plugged these things in here and ask how will Q topological go? How does Q topological, or what is Q topological for these boundary conditions? The answer is very easy. This is the question. The answer is Q topological equal to 0. Okay. So let us say that this for large r goes as this thing, but now these go as 1 by r power 3 by 2, 1 by r power 3 by 2, that becomes 1 by r cubed, but now this is a surface integral which goes like r square. Okay. So just simple. So basically what that tells you is that since goes like 1 by r power 3 by 2. So it falls off, and strictly remember this is really you have to put that thing and take it to infinity. Okay. So what it tells you is that you might think of configurations which have topological charge, but those cannot be realized in finite energy. Okay. So this is called I mean in some sense this is another way of understanding Derrick's theorem. So there is no conflict. So you so we saw this fancy thing, oh, so we thought we could get something to carry that charge. So but let us ask so when can di of phi go as, or when can q topological be not equal to 0. Okay, so just we go back and just like we did finite energy, we can ask what these things happen. So you can see here that let us say that phi goes to this constant, but di of phi, if it goes like 1 by r, then the r square can cancel and there is not even plus epsilon or anything. One, if it has a term which is 1 by r, you are in good shape. Okay, this can happen when okay, then there is a chance, but quite clearly this cannot happen with just pure scalar fields. Okay, so there are two routes to actually getting around this thing. One route is to add gauge fields, which is what we are going to do. The second route is to actually go ahead, change your Lagrangian, make it non-linear, then the energy etc conditions would be different. Okay, both routes actually work, and so that you can so implicit in Derrick's theorem is the fact that you assume that your kinetic energy is this. The scaling arguments, everything that we did really was based on this kind of Lagrangian. So if you work with nonlinear models, okay, so for instance if you put something like some function of phi out here which is such that it will force things to work out nice. Okay, but that's not something we will discuss right now. So the thing is, so what happens when we add gauge fields which gets around this. So let us do that. So first step is to replace this by covariant derivatives. Okay, and there will be one more which is minus 1/4 f mu nu a. So this would be the Lagrangian density. Okay, so this is what we started out with last lecture. So this exactly we recover that, but the thing here is this. So if you come back to the Hamiltonian density, again the same thing happens. This becomes this plus, we chose, remember A0 was 0, everything's were independent, so there is no electric thing. So again I am not writing this piece, but there will be a piece coming from Fij half probably Fij square. Oh, it is non-abelian, so I should actually be careful, I should write it like this. Okay. So now you look at this thing, u of phi, the requirement is exactly like this, but the change here is now that this got replaced, the ordinary derivative got replaced by the covariant derivative. Okay, but the topological charge still requires this. Okay, so now there is now you can see that what you need is something weaker. You can satisfy this provided the gauge field also conspires, the gauge field configuration, you also have that extra field, has a condition. Okay, so since di phi, or this was just what we wrote, pi mu a, what was that equal to? I just want to get some definitions correct. Okay, so this is the same as pi mu. Yeah, the most important guy, I forgot. Okay, So what this tells you is that you can arrange things such that a mu, so this goes like 1 by r, this should also go by 1 by r, but there should be this cancellation. So in other words, the 1 by r part of d mu of phi a actually determines the 1 by r part of a mu. Okay. Now coming back to, we still have to go back and check what about this. Okay. So if a mu goes like 1 by r, f will go by 1 by r square, it will go by 1 by r power 4, you are in good shape. So that does not still conflict, so there is no conflict, this term is goes to 0. Okay. So there is no conflict. So looking at this, so we need implies that in some sense a mu should go at least like 1 by r, and you do not have freedom with the coefficients in front of that 1 by r, it better be such that this cancels this. Okay. So I would recommend that you go back to the vortex example that we looked at and go through the same arguments, you will see that things work out. Okay. Even in precisely in the same fashion. Okay. So now that we understand that, so now the question is, we have added gauge fields, we are looking for configurations where mod phi square tends to mu square upon lambda and di of phi tends to goes to 0 as 1 by r for goes to 0, but it goes to 0 as 1 by r. Okay. So yeah, so these are the things, and so now the question is, how do we go about, so let us make some definition. So let us look at the, let us call the phi configuration, the configuration of phi at on S2 of infinity on the circle at infinity. There are only two variables, right, it is theta and phi. So we just call it something like phi infinity. So let me, I will keep going back and forth between the matrix and this thing depending on which is convenient for me. Okay. I will just call it phi a infinity of theta and phi. Okay. And further, so we want to ask what would be the contribution. So let us look at this integral. So what is happening here, we have taken a circle at infinity, so this I direction will be the r direction, and so these will become the theta and phi derivatives. Okay. So then q up to some factors we should define as integral over this thing which is d theta d phi sin theta, which is the angle integrations, that is the circular sphere at infinity, times phi at infinity. So yeah, trace of phi infinity times the, now the other ones are just d theta okay. This is it at infinity, of course. This would be the topological charge. Okay. And so now so now what I will do is I will fix this by taking the simplest configuration where I take phi. So let us do an example which I know is minimal charge, which will let me fix the constant for you. Okay. So the example, there is, so yeah, thank you. So, I need to antisymmetrize, but okay, that will just give me factors. So, I just put one of them, the other one will not contribute. Okay, so, I am just jumping some steps, is that correct? Okay, just let me get to the next step and then we will come back to this, we will ask. So, it is like what I have in mind is, if I have epsilon, no, maybe I should antisymmetrize, yeah, I should maybe write like this. Okay, if I am writing in matrix form, so that takes care of it. Okay. So now what we will do is so this is so what is because of this condition, it is like this is also so we know that this phi infinity of A is also a set of points on a circle of radius square which is mu square upon lambda, that is what we have. So, we can just go ahead and choose, for instance, let me choose phi of A to be square root or mu by root lambda okay, and choose it to be along the radial direction. Okay. So, here is a case where I am doing the soldering, this is also soldering, because A here as we started out was the gauge index or the SU2 adjoint index, but on this side this ER as a normal space vectors is 3 components, or if you feel uncomfortable with this I can just say that phi 1, phi 2, phi 3 is equal to mu by root lambda times how does it go, cos theta, no, sin theta, cos phi, sin theta, sin phi and cos theta. Okay. You will see why it is better to write it in this fashion. Okay. Okay. So I'll keep working in this fashion. So, what we need to do here is to work out what is the d theta and the dr d phi derivatives of this, but if you think in terms of unit vectors it is very easy, whatever you write here as d theta of this is e theta, and d theta d phi of ER is just 1 by sin, I think there will be a sin thetas will get cancelled out, whatever, I mean there will be a, so this will just become E phi. So, d theta of ER cap is just E theta cap, and d phi of E phi, no, ER cap is along E phi cap. There is no sin thetas etc., right, I mean I think it is okay, yeah. Okay. So now we have to just understand how this thing works. So this will this is this if you write out in terms of this thing, you will see that this particular term there is yeah. So this is so Q will just turn out to be integral d omega, where d omega is just this thing, times this is along up to the each of these will give you these factors mu by root lambda whole cubed times ER dot E theta cap dot cross E phi cap. Okay, that happens to be 1. Okay, so this is just so this will just give you 4 pi. Okay, so first thing we want to do is get rid of this factor, and we have to do this thing. So you can see now Q should be, now we can put equal to's 1 by 4 pi, and one way of doing this is to replace all these things by unit vectors. If you had just replaced this by the hat version of that, would have been in good shape. Then these will go away, 1 by 4 pi integral d 2 s I epsilon I j k Okay, now I fix the constant also. And so this will be up to a sign, it is 1. So for example, for this particular configuration I have adjusted it such that q equal to +1. Okay. So what this tells you is that if you want to get something which is topological charge 1, it also gives you some detail about what phi should look like. Okay. If you look at the ansatz of which was chosen by Hooft, it was just this x a by E r square h of r. Okay. So this is exactly, so at everywhere this actually goes to what am I trying to say? Yeah. So this is along the radial direction. It is exactly this, because I can rewrite this if you wish as root mu by root lambda, just to match this kind of convention, x a upon r. Okay. So it also tells you the behavior of h of r. So we can again go back and say that limit r tends to infinity, h of r should be such that this just becomes should go like E of r plus stuff. Right. So that this will match this. What? Oh yeah, yeah, sure. Yeah, the best solution is to go ahead and define this should be its behavior for large r plus subleading terms. Okay. So now we sort of so this gives us some intuition into the ansatz, which reminds me, by the way, there was a question yesterday asking how did Prasad and Sommerfeld discover the solution. Apparently I read I just reading somewhere I discovered there was a note which explained this. Apparently they were playing around with a numerical solution to Hooft's equations, and then they found this their solution, the hyperbolic solution, was looked like a pretty good fit, and then they sort of worked backwards and found that actually if you take lambda equal to 0, it is an exact answer. Okay. So that just explains this thing. Okay. So first thing is, now we need to, one more thing which we need to understand is what is the sense in which we know that when you consider a situation where the symmetry is broken, for in this case it is broken from SU2 to U1. Okay. So it is fine, but the question is how do you identify the U1? It was very simple when we just took the case of along the z direction or something, 3 component was non-zero and did the thing, it was fine. But here you can see that even on the sphere at infinity the direction is changing. So now the question is how do we identify, so how do we identify the U1 gauge field? So actually the correct way to do that is to go back and to ask what are the allowed fluctuations in some sense, and that is what we will do. What we will do is we will consider, suppose in a region we have not just we have phi such that mod phi square equal to this quantity mu square per plus lambda, and further di of phi also is 0. No need to write it like this, write the whole thing, d mu of phi is equal to 0. Okay, we saw it falls off as 1 by r power 3 by 2. Okay, so at infinity to so where we are trying to work out things is strictly it's close, I mean it's pretty close to 0 or 0 if you wish. So the question, this is where we expect to identify the U1 gauge field. So now the question is, if you look at this equation, this tells you that I can go ahead and solve for the gauge field in terms of the phi field. Okay, and this is also related to this statement which I made, that these things have to get related. Okay, so we will do it in this fashion and we will work out, we will see what is the most general solution to this. Okay, so but d mu phi is nothing but pi mu of a should be 0, and do we have an expression for pi mu of a? So this is what we get. So we need to solve this particular guy going to 0. Okay, and we are given phi, so we can solve. So in some sense we can, so if you look here, this phi, as long as this phi is non-zero, we can sort of pull it out and divide by and stuff like that and solve for it. We will solve for it soon. Okay, but key point here is that phi takes cannot vanish, which is true on this. All the I mean the full vector phi cannot vanish, that is what this is telling you. It has some fixed norm. Okay, so let us solve for this equation and see that we get some abelian fields. So what we want to do is to solve pi mu of a equal to 0. So what I will do this, I can take this to the other side and put a minus sign. So we have E epsilon ABC a mu b phi c equal to minus d mu of phi a in that region. Okay, so the region we have in mind is a region close to infinity, where we know that SU2 is broken to U1, everything is fine. Okay, but we still have painful factors of phi floating around, so we need to get around that. So first step to do that would be to get rid of this epsilon from here to that other side. So let us do that by multiplying this by epsilon, say a l m. Okay, so we have to use that and put this here 1 by e. So this just using the identity involving two epsilons with one contraction, this is just delta BL delta Cm minus delta Bm delta Cm into a mu b phi c should be equal to minus epsilon a l m d mu phi a. Nothing deep, I just have gotten rid of an epsilon, but now you can see there is some simplifications happening out here. This just tells you this is a mu l phi c minus I did something wrong, right? The something should be m. I did the opposite replacement. Okay, are we okay now? Good. Okay, so first thing you can see here is that because what you are seeing here, if you think in terms of matrices, this is just the commutator of A with phi. So obviously there is one piece which will give 0 to this, which is if I take a mu l to be, let me write something else, let me write little so suppose a mu l is some little a times phi l. It doesn't, it will give 0, that will cancel out. Then I should write another piece which will give this guy. So this should be something like minus L with some constant which I will fix soon, epsilon L A B phi a with some constant which I need to fix. I think it is a minus sign, we will fix this constant. Okay. So, we just plug this in here. Now, for this whole exercise you can see that this term just drops out. So, it really comes down to doing this thing again, but instead of doing that, can we just go back to the top expression which we just started out with and see that it works. That is all we need to do. Okay. Is this clear? I just go and plug this in here, and then I do not need. So, what I need to do now is to work out what epsilon, I have to be careful with indices. So, let us put d, and then I have a mu here as L, that is good, and is there any m's here? No. Okay. Epsilon dlm a mu L phi c should be equal to, let me call this constant alpha, so that I do not call every constant I write today as c. Okay. So, this will be minus alpha times epsilon dlm a mu L, which is this term, times phi c. Did I? No. Okay. So, I just need to again use this ad nauseum, this particular thing. So, alpha times, so this I can with I absorb the minus sign and bring L here. So, it will be d with a, delta d with a, and delta m with b minus delta d with b, delta m with a, times phi a d mu phi b phi m. Okay. So, there will be one term which is, yeah. So, let me just simplify that a little bit more. I need to write one more. I was trying to jump a step, maybe I should not. So, this should be alpha, should be. So, this will just make phi d phi b, is that right, minus this will give delta dB, that will make this d mu phi d. What should I do? I forgot something here, there is one more piece, d mu of phi b minus this term phi m d mu of phi a phi d. Okay. So, I get these two terms. First point is that this is 0, because phi b, this is nothing but d mu of phi b half, but that is a constant. So, that is 0. So, this term drops out. Phi m is mu square by lambda. Okay. So, we are done. So, alpha should be minus lambda upon mu square. Okay. So, now we can see that what we get is a mu L should be very nice lambda by mu square, lambda by mu square times okay. But in fact, you can see that I can simplify things. So, here you can see that this part is completely fixed, but there is a fluctuation which is just one vector worth of fluctuations. So in some sense you can see that morally speaking this is an abelian, in this limit this is an abelian gauge field. 1 by E, there is a 1 by E. Okay. In fact, we can simplify this expression a bit, we can get rid of this lambda mu squares if we work with phi hats, and we can just redefine scale A again, and the answer will be nicer with just 1 by E times this whole thing. But what I wanted to get through is that you can so this gives you a very nice handle on what the gauge field is. Okay. It also fits in with what I said yesterday, if roughly speaking if you did phi dot L will give you that fluctuation which is this guy plus, but there is this piece which you can't get rid of. Okay. So you can go ahead and compute f for this, f mu nu A for this, and from this, and then just define the U1 gauge field f mu nu to be just so let me just do one thing, let me just get rid of I want to get rid of these factors. So I will just make I will write a 1 upon E here, there is no problem with that, and this would mean just a new definition for A mu. Okay. So maybe I will just call this A mu tilde, and okay. So this is what I have. So you just define f mu nu as phi hat A f mu nu A, where f mu nu is given in terms of this. Okay. So this will agree, almost agree with what et Hooft wrote. He had some extra pieces, but those extra pieces were actually pi i's. Okay. So it is not written in that form in the assignment, but you can show that those two forms are equivalent. So this agrees with U1 with, if you realize that d mu of phi is 0. Okay. And if you just look through the structure, this guy will so we will see that f mu nu will have one piece which is plus the phi hat dependent pieces. Okay. So and this f mu nu has certain nice properties you can show. First thing you can show is that d mu f mu nu is 0. Okay. And you can also show that the Bianchi identity, which is epsilon mu nu rho d mu f mu rho equal to 0. Okay, where we have assumed that d mu phi etc. is 0, all these things we have, which is true. Okay. So you can go back and so this at this point actually we haven't made any assumption about the ansatz or anything. You can verify that the Hooft Ansatz actually gives this. Okay. So you will have to throw, I mean you should do some things with the k's and the h's that I leave it to you as an exercise. So that is another way of checking this thing. So you can see that what is happening, so all this analysis was done in a region quite far away from where the full gauge group could be restored. We needed phi, we needed this point that the phi was a non-vanishing vector, okay. And so this gives you a concrete identification of what the gauge field is, okay. So next class, I mean all these terms will be important. Next time we will see how the topological charge that we wrote out is indeed the flux, not the flux, I mean it's the magnetic charge if you of the monopole, okay. That more or less follows from what comes from here. So these pieces are important and we will see how that works, okay. So I stop here.